given a Lagrangian which looks like usual kinetic term plus some interaction term. We showed that there exists counterterms such that when we take the sum of all of the Feynman amplitudes has an epsilon to 0 limit. Let me just remind you that this W notation means it's some shorthand for expansion over diagrams. So it's sum over diagrams which are connected, which have and external lines where we put a h bar, the number of loops of the diagram, and then we have a Feynman amplitude where we have p on each edge and I on vertices. So this is just so as we explained at the very beginning, it's convenient to think of this as like the second order differential operator y contract with the propagator, and that kind of glues two vertices together along an edge. And here this means you think of this guy as being a bunch of vertices each labeled by I. So this is just the usual Feynman diagrams. Let's see. So the calculations we did earlier, so for example, let's consider the phi cube theory on Rn, and we'll expand as a sum where this I index refers to the number of external lines. So we saw with this very simple phi cube theory, we saw that the first counter term came from this diagram, I1, 1, and it looks like the integral of epsilon to the minus n over 2 times phi. The integral here. And then there was something from this diagram, I1, 2, and I actually don't quite remember what we got. It was some kind of complicated expression, but I think in dimension 4, it's it looks like log epsilon as an example. And we kind of saw how we can really explicitly compute these counter terms if we want to go through all the pain of various asymptotic expansions. So today I want to do two things. I want to try to address something people were raising last time. So normally you would say, if you read a physics textbook, they would say, studying the phi-6 theory in order to the 10 doesn't make any sense because there are too many counter terms. I want to explain how we see that that's true from the point of view we're taking. And the point of view I'm taking is not it's not unusual. This is the point of view taken by, say, Zamolodchikov in his papers. Or he's related to that, or by Wilson. Oh yeah, and another important part of what we showed last time was if we fix a scheme, by which we mean a way of extracting the singular part of a function of epsilon, then the counter terms are unique, provided they're purely singular. So I don't want to be too formal about what I mean by a scheme, but so there's some class of functions that can appear when you study this. There are always integrals of rational functions, so they're periods, some algebraic varieties. And you want to say, well, some of these functions have a nice epsilon to 0 limit. Let's look for a complementary subspace. It's a vector space, you can choose a basis, but it's a crazy choice to make. But once you choose that, then these guys are unique. So the first thing I want to do today is kind of rephrase this kind of inductive argument as a more abstract theorem. Yeah?
Mechanics question. There are two indices, the indices. They're accessed by JK. On copy. Okay, so.
Here? Oh. Okay. Was it a handwriting question? Okay. Yeah?
You mentioned it in the stat. Is it possible that if you add a counter term of phi to k, then it increases the singularity to cancel which you need to produce counter term of phi to k as well?
Well, I haven't, I mean, it is, but I think the standard treatment of this that you'll find in textbooks is, I don't like it, and I think it's wrong in some ways. It's not clear to me that if you start with a phi-4 theory, you don't need to introduce such a counter term. I don't care. I mean, that doesn't matter. The counter terms are meaningless. They have the counter terms have absolutely no physical meaning. There's no measurement you can make which will tell you what the counter terms are. What matters is things like the beta function. But if you go and calculate the beta function, as we will do later, you will find polynomials in epsilon do not contribute to the beta function. Logarithmic and polylogs will. So
is there any sense in which I can whether if I compute a Further function where the operator is separated by some finite distance, then these counter terms will not contribute to the Further function?
They'll contribute to an intermediate step of the calculation.
Right, but in the final product.
In the final product, no. I mean, I think your questions will be answered better in a few minutes. So like part of your questions is like, what you're saying is, you know, fixing a scheme, this is like a ridiculous choice. You never want to do that. Nothing meaningful will ever depend on a scheme. So we want to, what I'd like to do is phrase things in a slightly more abstract way. So I want to make the following definition. Scalar field theory on a manifold is a collection I, L, phi of functionals phi, which also depend on h bar. There's series in h bar. So we can expand it like this. Where ik L is homogeneous, so it's a polynomial of degree I. We think of it as having I inputs, like I external lines. Phi. So the idea is going to be that a theory is specified by these guys, which are the effective interactions. So it's a collection of effective interactions for each length scale. And what properties do we want them to satisfy? Well, we want them to be related by the normalization group equation. So let me write this diagrammatically so that I of L is going to be given by sum over graphs where I have epsilons at each vertex. And some external lines. Right, so the intuition is this is the effective interaction at some small scale, describes the scattering of particles where we just ask if they interact in some small region. And we get this guy by allowing more kind of intermediate interactions to build up the larger scale guy. Does that make sense? Or is that too vague? Yeah. Let me see if I can make that more clear. Epsilon is small, L is big. Actually, the formulas work even if that's not the case, but to understand what's going on, like that. Yeah, exactly. So there's also an infinitesimal form which is useful. me see if I can say a little bit more about the intuition. So I of L and I of epsilon are kind of both ways of encoding the same data. So here I want to say, suppose I want to encode my theory by saying, I want to consider fields which interact in some small region, size around epsilon, and that they propagate. So between these guys, if you recall that this guy is an integral from epsilon to L of the E kernel, I want them to move around, so to be particles moving around with proper time running between epsilon and L. Well, running, running bigger than epsilon. So if I want to describe it using I of epsilon, I have a small scale interaction, but then I can say, well, let's just re-encode. We can look at processes where they're allowed to propagate between these interactions with proper time between epsilon and L, and encode that in I of L. It's encoding the same data. Sorry, I didn't sleep well last night, so I'm being a bit vague. If we were to take a more momentum space point of view, we would say I of epsilon is a function, depends on the very high energy fields of some, up to some high energy scale. To get I of L, we would integrate out fields of some intermediate energies. And I of L would be describing functions of the fields of a lower energy scale. Now, what other properties would we like our family of effective Lagrangians to satisfy? Well, if we want I of epsilon to describe interactions between fields happening at a small scale, we'd want it to be close to being a local Lagrangian. So also, we require that this guy is, yeah?
On the right hand side.
Uh-huh. They're still ILs. So we, well, because we're differentiating, right? We're taking epsilon close to be just a little bit less than L. So this infinitesimal form was written down in some papers of Bolchinski. So the other thing we want is that we want this guy to be close to being local as epsilon is small. There's a couple of ways you could say that. Here's one. Just some technical details about how you might say it. Suppose this is something which has I inputs. I. One way to say it is, suppose that one input, suppose that two of these inputs were at different points in space-time. If, say, phi 1, say, phi 1 is equal to 0 outside some region, some ball, say, x less than 1, and phi 2 is equal to 0 outside x minus x naught less than c prime. So phi 1 lives in here, phi 2 lives in there, where these are just to find disjoint regions. Well, what you want is that as epsilon goes to 0, this quantity, if I have two of these inputs must go to 0. Because if I had a local Lagrangian and I had two fields which were supported in disjoint regions, it would just be 0. But this is something kind of quasi-local. Almost local, but maybe with some exponential decay. So then, let's go to 0. And in practice, it will go to 0 at some exponential rate involving an epsilon and the distance between them. Okay, so what we're trying to get towards is, things involving counter terms are kind of meaningless because they involve the choice of a scheme. So you want to have some more abstract definition of field theory where the terms clearly have a physical meaning. Here, we've defined our notion of field theory, the definition does not involve any UV divergences. The quantities involved all have physical meaning. UV divergences would only arise if we tried to take epsilon to 0, but we never do that. Because that's, we can never actually access infinitely small scales. So, the utility of this is that the construction of counterterms, then instead of being some kind of algorithm, it becomes the proof of a theorem. So a priori, we've written down a definition that we don't know there are actually any collections of effective interactions satisfying these equations. But constructions of counterterms tells us that that is the case. So, theorem. There exists a non-canonical. It's very important that it is non-canonical. Bijection between series in H bar whose coefficients are Lagrangians scalar field theories in this sense. So, in other words, we're giving some definition of field theory for which the space of field theories is of the same size as the space of classical field theories. Yeah?
Do we care about convergence?
It would be nice if we could understand anything about the convergence, but I don't. It's too difficult. Except in some isolated. Except in some simple cases, it's very, very difficult.
And the scalar field theory is also a form of series.
Absolutely, yeah.
Particular fields, these are not local necessarily.
Yes. By Lagrangian, I always mean local. Yeah.
So these are not the same things as the IL.
No, so there'll be a procedure to given a Lagrangian constructing one of those.
So what happens to the H dependence of the IL as L goes to 0?
Well, IL is a series in H bar, so.
I'm thinking that. So I was thinking that you generate the non-local terms by computing this kind of diagrams. This is H bar dependence.
Yes.
As L goes to 0, you get microscopic theory.
No, but you get all kinds of singularities, right? So you get also, I mean. So if you want to reverse, if you want to go from here to there, you would have to, in either way, you would have to do some kind of removal of the singularities. So as L goes to 0, you would get some series in L with all kinds of crazy singularities. And somehow extracting some finite term will give you back a Lagrangian. But the Lagrangian itself might depend on H bar. But that bijection is scheme dependent, not. So here's the proof. Given the Lagrangian, which we call it I, and view it as the interaction term, we're assuming that the kinetic term is fixed to be the usual kinetic term for a scalar field theory. We choose a scheme and let I of L be the limit so we construct I of L by taking our Lagrangian, removing the counter terms, and then summing over all Feynman diagrams in the usual way. So diagrammatically, this is some kind of sum where at each vertex we have I minus the counter terms. Now, it's kind of obvious that this satisfies infinitesimal orgy flow equation. We differentiate this with respect to L. We'll remove the differential with respect to L past this limit. The only dependence on L is there. So let me write that out.
Did you ask one thing that I of L depends on phi?
Depends on which, sorry?
Yeah, the I of L in bracket phi.
Yeah, so phi is what's labeling the external lines. I'm sorry if I'm dropping that dependence from the notation. So it's a polynomial in the field phi, or phi, and the degree of the polynomial is the number of external lines. So let's check that this guy satisfies the infinitesimal orgy equation. So d by dl I of L is lim epsilon to 0 d by dl so I'll just kind of sketch it out diagrammatically. Graphs. Well, you look at the only place there's any L dependence is in the propagator. So if I differentiate the propagator, I'm going to say one edge will be replaced by the heat kernel. And then this can be so then there's two possibilities. Either this is a separating edge or it's a non-separating edge. And we see it's the same. Okay, any questions about that argument?
We also summing over the internal edges now for each propagator.
Yes, so we each pop, but now we think, so we sum over the internal edges, and so I look at the complement of that internal edge, and I recognize that it's the same form as a thing defining IL at a different number of external lines at a different coefficient of. So if it's a separating edge, I get 2 copies of it, of IL, and if it's non-separating, I get 1 copy. Now, it's also, so we wanted to say that this was also local, that if L was really small, then this thing looks like something which only, there would be 0 if these 2 copies of these phi's had disjoint support. And you can kind of convince yourself that that's the case, just because if L is really small, then this propagator has exponential decay outside of some small region. And this is local. This is kind of close to local. It's in radius around L. So the whole thing when I build up the diagram, I get something whose support is of radius around L to the number of edges. So some finite distance. So that's so. And for the converse, we say, well, how do I know I've got every collection of effective actions this way? What if I'm missing some? But there's a simple argument using, again, the infinitesimal order flow equation, which tells you that you really do get everything this way. See, so this I as a function of L is it's not the local Lagrangian. No, it is the same. It's the same. So I want to say, so I have a function of L which is like a non-local thing, and so we give a definition of a field theory as saying it's a collection of these I of L satisfying some properties. So, but how do we know there are any solutions to these equations? So here I want to show that there are solutions to the equations, that there are the same number of solutions as there are Lagrangians. So for the converse, if we had I of L and say I tilde of L such that I of L or S is equal to I tilde of L, or S for K and S equals K. So we want to show, suppose we have 2 collections of theories which agree up to some term, up to some order in H bar and some number of external lines. Then we want to show that they differ by a Lagrangian. And that will tell us that actually everything arises from a Lagrangian. So the difference between them must be a local Lagrangian. And why is that? As, well, if we look at the derivative of the difference between them, in each case, the derivative with respect to L is expressed in terms of the I or S for lower order. since we've assumed that these guys are actually the same at lower orders, this derivative must vanish. Now we also know that for L small, each of these guys looks like they're local. So if we have something independent of L, which for L small is local, it must just be local. So this is how we know we get everything, every collection of effective interactions. So order by order, we do an inductive argument. Suppose by induction that we have everything at a lower order in this I and k. Then at order I and k, we must get everything by. Because by this. Okay, so any questions? So maybe I shouldn't have gone into quite such detail about the proofs, and I want to return to the kind of questions that Hafiz was asking. And there'll be a lot of questions about last time, about why can we talk about the phi to the 10th theory or something like that, and why are there counterterms? Well, so I think part of the issue is that some of the quantum field theory textbooks may not have absorbed the way more modern points of view in field theory that so there exists an infinite dimensional manifold of quantum field theories. Now, you can try to define this infinite dimensional manifold in any axiomatic scheme you prefer. Some people might like to say the Hilbert spaces for every Hilbert spaces and time evolution, and other people might talk about correlation functions. Here we've talked about effective interactions. One will hope that every set of axioms will lead to the same manifold. Now, this manifold is just kind of God-given thing, independent of any correlation functions, or independent of any counterterms or anything like that. So in our setup, it's given by a collection these effective interactions. So choosing a scheme gives coordinates. So we've seen that if we choose a scheme, a way to extract a singular part of functions of epsilon, it identifies the manifold of quantum field theories. Say, just focusing on quantizations of scalar field theories in our setting, collection of Lagrangians. And because you can just write down Lagrangians, we have an explicit description of the manifold and we've given coordinates. But then the nasty part is when you're trying to communicate with somebody, you never really want to talk in a scheme-dependent way. Because what if they chose a different scheme? Changes of schemes will give you kind of crazy coordinate changes. Like super, super complicated coordinate changes. So you never really want to talk about what happens in a particular scheme. So how do we find how do we talk about a particular field theory? I mean, so it doesn't really make sense to say, I will choose my scheme, which gives me some coordinates, and I will talk about the field theory specified by the coordinates in this scheme. That's not really a sensible thing to do because these coordinates are not really meaningful or intrinsic coordinates. So, field theories can only be specified by symmetry properties so you could say you might be lucky and you might find that there's a unique field theory with certain symmetry properties. But most of the time, the most important symmetry property you will care about that will allow you to specify your field theory is given by scaling of spacetime. We consider translation invariant field theories on Rn. And I'm really going to focus on things given by a quantization of a scalar field. Then, or something with the kinetic term. So, such theories are acted on by scaling of Rn. Like so this field phi has some dimension, which is needed to make this quantity scale invariant. And if I scale my field, it gives an action
pretty clever in the scaling because the light is specific to a scalar field.
Yeah, you figure, I mean, any, yeah, you can figure it out just by saying, well, there's a volume form, just dimension n, and there's two derivatives, and then there's two fields. So the Wilsonian philosophy is that you have this kind of abstract manifold of theories. The things you're going to care about, the only way you can really specify a point, it's not so much by specifying a Lagrangian, because that's scheme dependent, it's coordinate dependent, is by studying symmetries of the theories and this flow. So good theories live on a trajectory to a fixed point. So a fixed point, as we scale, kind of look at things at a smaller scale. And so what's nice about this is that in almost all cases, there's going to be a finite dimensional space of good theories. So what good is be complete or normalizable. There's going to be kind of subtlety about this that we'll discuss shortly. So the typical behavior so at the fixed point, given by the free theory, the fixed point, say I call it P, well, the space of field theories is infinite dimensional, but I can look at the tangent space at this fixed point. The tangent space at P to the space of theories so because it's a fixed point, it has an action of this vector field, and I can decompose it into eigenspaces. So this has finitely many negative eigenspaces corresponding to directions where if I move a little bit away, I'll come back to the UV, and infinitely many positive. So I had a number of questions about, like, well, how can we define theories like the phi to the sixth theory in O4 or something with something which is not traditionally normalizable? And so what we're seeing is that the answer is not that that theory does not exist. It's that there's too many possibilities. There's no good way to specify a theory like that. There's only going to be a finite number of theories which will flow to a fixed point, and those will be the ones that are traditionally seen as normalizable, phi to the fourth theory in O4. phi6 theory in order 3, and so on. So
it's supposed to express some philosophy about nature, that like whatever theory we make describes the real world is supposed to be unique. There's supposed to be like something.
yeah, exactly. There's two ways to yeah, exactly. So one way to say it is, you know, if it doesn't go to a fixed point as you zoom in, then like, oh, this is the problem with gravity, for instance. Gravity is not normalizable. As you zoom in, the coupling constant gets bigger, and the fluctuations of the field contribute more and more and more and more. So it just becomes crazy and singular and badly behaved at small scales. So the converse to that is that if suppose I'm at a fixed point, this is the free theory, and here I have a UV complete trajectory. Now, suppose I decide to move a little bit off that UV complete trajectory, and then I want to imagine what happens at microscopic scales. Well, if I move a little bit off, I'll get a trajectory which goes to infinity that way. This way, it converges to the trajectory I started with. So actually, if I'm on a UV complete trajectory and I move a little bit away, I change my theory in a way that I can't even detect at microscopic scales. So this is another way of saying why these are the ones that are physically important. And I think in their condensed matter literature, they would emphasize this point, that there's some universality class. It doesn't matter what happens in the microscopic scales, everything converges at large scales to the same thing. That defines the universality class of a theory.
Is that a way to define something like that?
That if I move a little bit off, I'll come back? No, it's gonna follow from the fact that it's just gonna be some silly property of the vector field, and that like if I'm here I'm moving off in a repelling direction. So if I move that repelling direction up here, as I move this way, it's going to repel. So as I move this way, it's going to attract. Yeah.
QCD a good theory sort of?
Yes.
But it's asymptotic freedom.
Absolutely. Asymptotic freedom is the same as UV complete. But it doesn't actually, no, asymptotic freedom is weaker than UV complete.
I'm sorry?
I mean, it doesn't have to flow to a free theory, it has to flow to a CFT. That's what UV complete means. But a free theory is a CFT. So. Okay, any other questions? Maybe let's just spend 5 minutes figuring out, like, what are the good theories on or for classically? I mean, everything I've said about the action of scaling, that's something you can also say for classical theories. So it's a good place to start to figure out what's going on.
What we had there was if we took the UV complete trajectory and jumped a little away from it. If we were at the free theory, we jumped a little bit away from it, is there any guarantee that light will converge to some UV complete trajectory, or could it just go completely straight back?
Well, if we're at the free theory and we converge a little bit away, then it's something that in the UV would just kind of fall off, but in the IOR would come back. So we get something that would come back to the free theory in the IOR. So, right, so let's draw the vector field. It has some, let's draw the vector field so that the arrows point to the directions things flow in the UV. So it has some attracting and some repelling directions. But so if this is the free theory, so the UV complete trajectory will be this one here or this one here. So if you're saying, what if I went up there a little bit, then in the IOR, I would go back down. If I went up there a little bit, then you see from the trajectory that in the IOR, I would just go back over here. But as you see, it goes to it does indeed. If I go in some direction which is not in an eigenspace, then
you'll limit to some.
Yeah, I'll kind of project onto some UV trajectory.
You see the condensed matter, they look at the other limits?
Yeah, exactly, because in condensed matter, you assume that there's some kind of granularity, that there's some fundamental scale. So you don't really care about things breaking down in the UV. Well, what they say is that in the IOR, if I go the opposite of the arrows I've drawn, they say, well, here, all of these trajectories, they look the same in the IOR because they converge. So they would say that a trajectory like this one, what I would call a UV complete trajectory, they would call universality dense.
Does it then have like infinite range? Or like this is the opposite to.
But though they have infinitely many, but what they're saying is like if I just move a little bit, it doesn't matter because as I go further out, I just come back to where I started with. So that these are like irrelevant deformations. So let's consider classically there's a scalar field theory on Rn or 4, and we look at SO4 symmetry product translation invariant Lagrangians. So we consider the free term, then phi as dimension one. Yeah, it is the same dimension as the L1 form, and that's enough to make this kind of thing converge. Because it's two one forms and two derivatives makes it look like a 4 form. So let's think about it. So what are the dimension 0 Lagrangians? Will give us UV complete trajectories. So what are they? So integral phi to the 4th is a dimension 0 because I have 4 of these guys and I'm integrating over all 4. So this is the right kind of thing to be in. One can integrate. Is a dimension 0. equal phi cubed. It's dimension -1. Dimension -2. And if you want to consider things being SO4 invariant, these are the only possibilities. Because if you wanted to put in some derivatives, that would push the dimension up by 2. And this one needs to be reabsorbed. If I put in some derivatives, I mean, the only SO4 invariant derivatives would be the Laplacian, so I needed these 2 derivatives. So that would put the dimension up here by 2, and here I would just recover this term, which I already have. So these are the only possibilities. So let's put in the powers of the scale. So as I classically consider the orgy flow with some scale, this is dimensionless. This would have a scale. So this guy, so the IOR would be mu to 0. No, sorry, IOR is in UV. Is 0. These terms would dominate in the IOR.
So mu is like the coupling constant for this thing?
You could say that there's 3 coupling constants. I'm telling you classically how each coupling constant scales. They get multiplied by the scale. Some power. Let's see. I guess maybe we'll stop there. Next time we will figure out quantum corrections to the orgy, to this orgy flow, to this beta function. And yeah, and we'll. Unless there's any questions?
But if you add a correction, the coefficient does apply to before it goes to infinity.
Yes, that's right. So that's I meant that. The 5 4 theory is not strictly speaking a UV complete theory. So if you this coefficient here will become like h bar times the logarithm of the scale. So when you work in perturbation theory, h bar is a formal parameter. You don't really know if it's positive or negative. So there's a kind of a cheating workaround to define perturbatively normalizable. It's to say that in the UV, like if you have a bad term like 5 is sixth, this will have a mu minus 2. So a really bad term like this will have, in the UV, will have polynomial growth. But a term like this, which is marginal, will have only logarithmic growth. So when you work in perturbation theory, in h bar, it's consistent to say you don't want to look at things which strictly flow to a fixed point. You want to look at things which only have logarithmic growth. Maybe they flow off, but not very fast. If you try to resum, if you resummed up these things, it might become h bar to the mu, which might become polynomial growth when h bar is an actual number.
Comment on the number of the relationship within S matter is number of universality classes versus the number of theories in dimensions.
I think that will be the same thing, right? I think, yeah, they might, in condensed matter, you might study theories with less symmetry because they don't care about Lorentz symmetry. But you know, if you're studying the same type of theory, it will be the same thing.
You can choose to study the ability scale,
Yeah, so I think you should find like the number of universality classes, which the IR is like the same as the number of trajectories, which will do at this point.
So this renormalization flow depends on sort of this scaling symmetry.
Yes.
So if you were on an arbitrary manifold, do you always have some symmetry like that? Does it just change the volume of the manifold or something?
Well, that takes your manifold to another manifold.
Yes.
So if you suppose you had a theory defined on a Riemannian manifold, and you do this, you get a theory defined on a different Riemannian manifold. It's hard to compare them.
Yeah.
So this is only something that can work when your manifold. I mean, what you need is a manifold with a symmetry and a free theory, which inherits that symmetry. So
the whole concept of this renormalization, you're just like very special about theories on Rm that are free term plus interact.
It doesn't have to be free term personal interacting with them, but I mean, the way I think about it is definitely something about theories in Rn, because Rn has a symmetry. I mean, there's another way you might also think that, like, suppose a theory was something you would assign, you could put on any Riemannian manifold, which might be that. In that case, the set of Riemannian manifolds has a symmetry by scale and metric,
right.
And then you'd be in a good situation too.
Yeah, okay, that makes sense.
What's it?
Scalar field theory is
Yeah, exactly. Yeah.